easiest thing is to see visually that here's one little 1.5 pi. You wind up here. Okay? Yes, ma'am. Absolutely not. There should be the bucket, but it was online. Anyway, when you go there, since 3 pi over 2 is within 1 revolution, all you have to do is add 2 pi and subtract 2 pi. And if I'm adding 2 pi to this, the easiest thing to do is just add it in terms of 4 pi over 2. Then I think 3 pi over 2, and I subtract 4 pi. And why I'm doing that is because I'm just keeping it from common denominators. So my positive coterminal would be 7 pi over 2. My negative would just be negative 1/2 pi. Okay. And that's where people get weird with that. And I was helping the girls with that one earlier. We did an example of 17 pi over 4. Everybody okay that 17 pi over 4 is beyond 1 revolution? Okay. 17 pi over 4, if I write that as a mixed number, is 4 and 1/4 pi. Be okay with that? Yeah. Now that tells me how many full revolutions do I go through before I land at 1/4 pi. I go through 2 of them. So if I graph that, we go 1 little, 2 little, 3 little pies, 4. There's my 4 pies. I went around twice. Now, wherever I place my angle after going 2 full revolutions means that I'm now within 1 revolution. Basically, what I'm doing, all right? If you have water, you have to take a drink. You're welcome. At this point, I know that I have to go up a quarter. Now, where does the quarter wind up? Well, it winds up halfway between 0 and a half. There's my pi over 4 value. So what I'm thinking here, since this is beyond 2 revolution, what we can do is, well, you could just back out 2 twice, you wind up at pi over 4. There's your positive. So I'm within 1 revolution. Then I subtract subtract it again. And I wind up with negative 7 pi over 4. Those would be my positive and negative coterminals. Yes, ma'am. Since I'm beyond a revolution twice. 4 pi means I spun around 2 times. So I had to back it out. I just back it out to be within 1 revolution. Remember, the easiest thing to do is figure out where your reference, this is called reference angle. Plot it, so then your reference angle, when you see it, you know that that angle, if you start at 0, winds up, and then you'll be within 1 revolution. Holy, what do you got? I'll get you next, Steve. I did. I just wrote it down. I subtracted 2 pi. If I go the other direction, I'm just going up to here, and that's negative 7 pi over 4. I just wrote down the answer. I just subtracted and wrote it down. I didn't plot it. You know what do you got? Yeah. And like I said, I just write it as a fractional amount and just keep going. Okay. Make sure your names are. Send that up, and we'll talk a little bit about where we're at with 13.3. Oops. And this kind of goes from some of the stuff we talked about yesterday. So yesterday we talked a little bit about plotting angles within that unit circle. And this kind of stems back from where we were at a couple of days ago. Back in section 13.1, we did this problem where we said cosine of theta equaled 3/5. You guys remember that? And when we did that, we said that the cosine of an angle was 3/5, which meant that the
I don't have it's gonna be the only one. And then I have dance.
Anyway, so when we did this the other day, we did this and then we said, hey, what is the cotangent of theta? So what you guys did is that we drew a quick, excuse me, we drew a triangle. We said if theta was placed here, my 3 is my adjacent, my 5 is my hypotenuse, and then that made my opposite what? 4. Okay. Made my opposite 4, and then you guys said, okay, if cosine was 3/5, cotangent would be how much? You remember what the ratio was for that one? Well, what's cotangent is the opposite, is the inverse of what? Tangent. There you go. So the inverse of opposite over adjacent would be, so cotangent here would then be 3/4. Okay. Now what we're going to do today is take that. What's up?
What's up?
Again? So what we're going to do today is that we're going to take these values and we're going to change it up a little bit. We're going to say that, bless you, we're going to say that we have an ordered pair this time around. And when you have an ordered pair, we'll make it really easy. We'll go with, again, with that 3 and the 4. If I have the ordered pair 3, 4, what quadrant does that lie in? 1. Good. So what we did here was we would plot out your x value and your y value. 3 and 4, and we put a point. You okay with that? Okay. Now, if I draw this from the center, from the 0, 0 out, that creates the terminal side of an angle, doesn't it? The terminal side of an angle lies at the point 3, 4. So here's the theta. If I place theta at the origin here, the theta value is looking at what value? The x or the y value? It's looking at the y value. It's looking at the vertical, isn't it? It's looking at the y value. So my y value is 4. My x value is 3. What's my hypotenuse? 5. Good. If I do it here, if I go -3 and +4, what quadrant does it go into? It goes into quadrant 2. The x value is 3. It's -3, excuse me. The y value is still 4. And then you still have, remember how we talked about the idea of this reference angle? That value of this reference angle is always going to be the distance from your hypotenuse value down to the x-axis. You still have this theta value placed here. It's your reference. What's that reference angle looking at? It's looking at a vertical still, isn't it? Your vertical, your y value, 4. What's your hypotenuse here still going to be? Still going to be 5. You're using Pythagorean theorem, you're still going to get 5. Because as you go through, and if you really got fancy schmancy with this, well, if it was drawn, that's just a bit better. If it's drawn just a little bit better, will that 5 value ever change? No. What's that? It's the radius, right? Because what's happening here is, if I have theta placed here, theta always looks at its opposite. What's the opposite always going to be? In this case, it's always vertical. What value in an ordered pair is always your vertical? Your y value. In trig function, what's always your opposite when you find it with theta? It's your sine value. So what happens here is that you get your ordered pairs, your x and y values become cosine and sine. So as you go through and start looking at this, you're going to get theta placed. When you place theta at the origin, your x value is your cosine. Because your cosine of theta is always going to be your x over your r. The cosine of theta is your x value over r. Your sine value of theta will always be y over r. Oops. If I look at theta here, and I want to write it in terms of x's and y's, what would tangent be? It's y over x. Because when you're at theta, it's your opposite over your adjacent. Your opposite is always your vertical. Your tangent will always be y over x. Which means if I have cosine is x over r, what's the inverse of cosine? R over x. But what's the trig function that's the inverse of cosine? Secant. Excellent. So that means you have secant values that would be r over x. Cosecant values would be r over y. And cotangent values that are x over y. What happens here, guys, is that as you go through and move throughout the quadrants, the only thing that really changes up are your sines, your SIGNs, because that reference angle will always be the same no matter where your ordered pairs get placed, because your radius won't change out of any ordered pair. Okay? It never changes. Whether it's with these style ordered pairs or if we get into the unit circle stuff, it doesn't change. Okay? Let me show you another example of where I'm getting at with this. Yeah. I have -12 and -15. I'm going to plot that, and I'm going to write out all 6 trig functions that have a terminal side located at -12, -15. What quadrant does that go to? Third, very good. If we ignore him, will he go away? Oh, it's that's not what we're down. What do you want?
Go.
No, I don't want to
go to class.
This might bring back bad memories, but I don't know. No, you'll be fine. What quadrant does that go in? Oh, I remember this. Which is quadrant number? Good. So we count out. A little 2, little 3, little 5, 4, little 5, little 6, little 5, a little 8, little 10, little 5, 10, little 12. I got it. Sorry, I got it. You were talking, I couldn't count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's close enough. Squint. Anyway, so there's my terminal side of an angle. It moves up here. If my terminal side of an angle is placed there, where do I locate theta? Where's the reference angle to that? The origin between the origin and the x-axis. There's theta. I draw that in, and I've created a right triangle. The right triangle I create, it's just telling me that my side opposite me is -15. It moved downward -15. The horizontal run there was -12. How do I figure out the radius? Right there. It's not a triple. You're thinking, yeah, that's the trick. It's not. It's that you're thinking 5, 12, 13. This is 12, 15. Nope. You're thinking that it's a 3, 4, 5 multiplied out. If it was a 3, 4, 5, this would have been 3 times 4 is 12. Then it would have been 4 times 4, so it would have been 12, 16. So in this one here, you have to multiply it out. I think you get some weird square root, and then you put that in the calculator and you do your over y squared stuff. I believe it's 3 root 41.
So this is
Go to your y equals and do the whatever that number is divided by x squared. I tend to keep these things the ones that are a little bit I believe it's 3 root 41. Can somebody verify that? Okay. So it gives you a radius then of 3 root 41. Now, earlier we talked about this being positive, positive, negative, positive, negative, negative, and positive, negative. Everybody okay with that? Now that means x and y are both positive. It means x is negative, y is positive. X and y are both negative. X is positive, y is negative. Will your radius ever be negative? No, it can't be because you're using Pythagorean theorem to find it. Okay? So that means, like we were saying, your cosine values and your sine values, cosine is positive, sine is positive. Cosine is negative, sine is negative. They're both negative. And then positive, negative. So if I start listing out my 6 trig functions at that value of theta, I always like to start with cosine because I want to go alphabetical. I know a lot of you guys will say, oh, it's sine, cosine, tangent. But remember, if you get in your mindset that it's cosine, sine, then tangent, you'll remember that it's going to be x, then y, and then your combo. It's just a little trick. What's the cosine of theta here? You don't have to simplify yet, but what's your cosine of theta going to be? Yeah. So it'll be negative 12. Cosine of theta is negative 12 over, what is it, 3 root 41? Which means we have to do what to it? Simplify and rationalize. Because we don't want roots in our denominator. The simplify part's easy. What's negative 12 over 3? Negative 4. And do you guys remember the trick when you have a radical in the denominator? Yeah, so it's just going to wind up being, if I simplify this out, I'm just going to wind up with negative 4 root 41 over 41. Does that vaguely ring a bell for quickness? Too much?
No. But it's still in my head, so
thank you.
Bye.
See ya. Have a good one. I got a compliment. Did you guys hear that? No pie for you. Why wouldn't I be wearing a pie today? Why not? No, I thought I'd wear a pie medallion. Did you just now notice it? At some point in time, you gotta realize you just gotta roll with the things that I do. I might walk in one day with flip-flops and shorts on. You wouldn't even be like, oh. All right, anyway, what's the sign of this? Very good. So the sign here, I'm going to not rationalize it yet. Just write it out as negative 15 over 3 root 41. And just like you said, it was negative 5 root 41 over 41. You all right with that? Tangent. Now, tangent's going to be opposite over adjacent. Tangent is always y over x. Our y value is negative 15. Our x value is negative 12. What's a negative divided by negative? Positive. So that tells you that tangent is going to be positive in the third quadrant. So tangent, negative 15, negative 12, which is positive 5/4. And that's the trick. Tangent will always be positive when the signs, SIGNs, of the other trig functions are the same. So tangent is positive in the first quadrant? Yes, sir. So let's talk about signs, like the signs they're positive and negative signs, not SINE. And then tangent will be positive in the third quadrant, but tangent will be negative in the second and fourth, because they have different signs, SIGN. And what do you think happens with the reciprocal properties for their signs, SIGNs? They're going to be the exact same. They're going to be the exact same. Okay. So if I'm looking at this cosine, sine, and tangent, I'm putting it on a clean one here so we have a little bit of space here. If I do that, the cosine, sine, and tangent, and I want to write out secant, or secant, cosecant, and cotangent, all I have to worry about doing, yes sir? Secant, cosecant, cotangent? Inverse trig properties. We're getting there. We're just introducing what they are. Okay. Basically, what the inverse trig functions are going to allow us to do is do twice as many solve for x problems and twice as many graphs. I'll show you. We're not there yet. I'll show you what we're going to do. It's really cool. So here's the deal. Anyway, when we wrote down cosine of theta and we simplified it out, we had it as negative root 41 over 41. If I flip that, I get 41 over negative 4 root 41, and then I'd have to re-rationalize it, wouldn't I? So here's the trick. Anytime you have a trig function that originally started with the radical and denominator, bless you, go back to that part and flip it first, because you'll have less rationalizing to do. So we started out that cosine was negative 12 over 3 root 41, or better yet, negative 4 over 41. Excuse me. If I flip that, it's root 41 over negative 4. Or you can put the negative in the numerator. It doesn't matter. It all works the same. Okay. Cosecant, same idea. It's the inverse of sine. Our sine was negative 15 over 3 root 41, which means it's negative 5 over root 41. I can write that as root 41 over 5, negative. Then lastly, our tangent was 5/4, which means our cotangent will be. There you go. And that's how you work with trig property. How do you find the 6 trig functions given the terminal sides endpoint? And it builds it out. And that's how trig works. It's built off of right triangles. More specifically, as we get to it more tomorrow, the specials. Right. The one thing that we didn't talk about yesterday, when we made a couple things up on that unit circle thing, we didn't talk about things called what I'll call what they're defined as quadrantals. When we did this yesterday, you either in your notes or whatever, I'm going to do something with them. So you might want to just make a quick circle and just relabel. Now, yesterday when we started our circle, we started at 0. We went all the way around to 360. Everybody okay with that? Yeah. We wrote half of 360 at 180. Half of 180 was 90. Added 180, we had 270. And then we switched all of those into radians. We put them in terms of pi. Remember that? So you start at 0. Full circle was how many pi? 2 pi. Half of 2 pi was pi. Half of a pi was, and then if I add a pi to that, I get 3 pi over 2. Now, here's the thing that's a little bit different from what we were at yesterday. Today, we started placing values that had an endpoint somewhere. It had a specific theta. That radius was dependent upon the Pythagorean theorem that we did. Now, what happens when your radius? Yes, ma'am. What? This? Oh, sorry, that was an R. Radius. Sorry. I said the word radius. Couldn't you hear it? No. For our Reva dirt sheet. So the reason why we call this thing the unit circle. The reason why we call this the unit circle is because you could call your radius really anything you want. So if I start here and I move it here, I'm going to say my radius is 1. Okay. If I say my radius is 1, and there's a reason why we use 1, and I'll show you here in a second. If my radius is 1, how far did I move from 0 to this point? To the right. I moved it 1. Okay. So that means my ordered pair here is at 1 for x, and what's my y value? 0. Now, in this case here, that means that my x value and my r value are the same. I moved over 1, and it's the same distance as my radius. If my radius was 5, and I moved over 5, how far did I move over x? 5. What's 5 divided by 5? 1. That's why this always works. Now, if I move up, what's my ordered pair? 0 and 1. If I move left, what's my ordered pair? If I move down, what's my ordered pair? So these 4 ordered pairs are the ordered pairs at the specific quadrantal. Now, 2 minutes ago, we also said that your ordered pairs meant x, y, which meant cosine and sine. Which means, what's the value of cosine at 0? 1. What's the value of cosine at pi over 2? 0. What's the value of cosine at pi? -1. Devin, I posted the assignment already. If you need to watch the rest of the video, it's already up there, buddy. Coolio. What's the cosine then at 3 pi over 2? You go back to 2 pi, you're at 1. Do that with sine. You start at 0 with sine. What's your sine at 0? Pi over 2. The reason why all of this works is because how long does it take you to go around a circle? You start at 0 and you end at 2 pi, right? What's half of 2 pi? What's half of pi? What's halfway between here and here? Aren't these points parts on the quadrantal? Okay. The maximum value for x is 1. The minimum value for x is -1. If you start at 0, what's your value of cosine on the quadrantal? What's the value for 0 on your quadrantal? It's 1. So cosine at 0 is 1. Cosine at pi over 2 is 0. At pi, it's -1, 0, and back. At 0, what's your cosine? At pi over 2, what's your cosine? You just wrote it down. At pi, what's your cosine? At 3 pi over 2, what's your cosine? At 2 pi, what's your cosine? It's oscillating. It's oscillating. It starts at 1, goes to 0, -1, back to 0, goes back to 1. Watch what happens with sine. Where does sine start at 0? 0. At pi over 2, what's sine? Sine and cosine are just continuous curves. If you take a circle and you go from being a round and you put it into a linear part, this oscillation occurs. Sine and cosine oscillate around the unit circle. When you look at sines and cosines, it allows you to do these types of graphs. for another example real quick, if I look at the sine curve here is the one in red. Are we okay with that? Now, what is reddish? If whatever, it's this one is the sine. Okay. Now, what's the inverse of sine? Cosecant. Okay. So if I'm thinking about this, if sine of 0, sine of 0 is 0 over 1, because that's what the ordered pair tells me. The cosecant of 0 would be the reciprocal of that. What's the reciprocal of 0 over 1? Good, it's 1 over 0, which is undefined. Okay. If I do the sine at pi over 2, the sine at pi over 2 is 1 over 1, your y over r. Bless you. What's the reciprocal property of sine? Cosecant. The cosecant of pi over 2, well, it's the reciprocal of 1. 1. Bless you. The sine at 3 pi over 2, okay, I got myself, at pi is 0 again, which means the cosecant at pi is undefined. I go to 3 pi over 2. The sine at 3 pi over 2 is on the quadrantal, it's on the y-axis, and it moved down -1. What's the reciprocal of -1? -1. Trig functions for sines and cosines and their reciprocals. And what happens is they oscillate. They are continuous functions all throughout. When you do the reciprocal properties, how do you graph an undefined? You do. But what happens if you have a 0 in the denominator? Vertical asymptote. What's the reciprocal of 0? Undefined, we just said this. So here's an asymptote. Here's an asymptote. Here's an asymptote. What's the reciprocal of 1? 1. What's the reciprocal of -1? -1. Somewhere between 0 and pi over 2 is 1/2. What's the reciprocal of 1/2? Somewhere over here, there's also another. Somewhere in here, there's something like that. Here's cosecant, does this. We'll get there, but what? And everybody gets to that point like, oh crap, that's all this is? Yes. It's literally ordered pairs, guys. It's ordered pairs on a circle. And we start with all of this as nothing more than these 4 ordered pairs do all trig. All trig graphs, sines, cosines, tangents, as we get to graphing these things. Everything is based off of a quadrantal. And that's how it works. Yes, ma'am? That's cosecant. We'll get to it. We won't get to graphing those things until after spring break. I just want to show you the importance of understanding why quadrantals work is because you can do all of that. Yes, sir? No, it has to be. It has to be because, good question here. Will we ever have to worry about the hypotenuse and not on the origin? No, because every ordered pair says that it is the terminal side of an angle lies at such and such a point, which means that the terminal side has to be placed at the origin to make it work. And you can't do it otherwise. Okay, so that will always go like that. All right. This is what we're doing, guys. We're just getting ordered pairs, we're writing out how do you get your 6 trig functions off of it, and then just practicing some reference angles. What you'll wind up doing tonight is going to look like this. You're going to be doing, oops, hold too far in. You guys will be working through, I guess I need to look at that. I'm going to give you an ordered pair of 1, -3. Write the 6 trig functions that will occur at 1, -3. Plot your ordered pair. Use Pythagorean theorem, find your radius, and go through it. Yeah, it's super easy. It's super easy. Okay. Oh, I skipped it right down. Sorry. Anyway, I put it online already. Both of those, please. I can't hear you. It's in the back, otherwise it's posted. There's in that little black bucket. I swear I keep all the spares if you need one.